Welcome to the deep dive. We take complex topics, sift through the information, and pull out what you really need to know.
That's the plan.
Today, we're looking into something that sounds a bit out there, but is actually having real effects right here on Earth.
Yeah.
Space weather. Honestly, I'm really curious to get a handle on this.
And that's what we're here for. We'll unpack what space weather is, where it originates, which isn't always just the sun, interestingly enough.
Oh,
Yeah. And its impacts, which are surprisingly broad, affecting our tech. And of course, how we keep tabs on it all. Goal is to get you up to speed, quick but deep.
Okay, let's unpack this. So, space weather. First time I heard it, my mind went straight to, I don't know, sci-fi stuff. Cosmic storms, maybe. What are we actually talking about here?
It's a good question because, yeah, it sounds dramatic. Let's say the official definition, like the one ESA uses, calls it the physical and phenomenological state of natural space environments.
Okay, that's a mouthful.
It is a bit dense, isn't it? Think of it more like trying to forecast the conditions in space. You know, predicting how energy and particles from the sun and elsewhere will interact with planets, with our satellites, with astronauts.
Ah, okay. So it's like Earth weather forecasting, but for space.
Exactly. It involves a ton of observation, monitoring, running models, trying to understand and predict the state of the sun, the space between planets, and critically, any disturbances that might impact us down here or our technology up there. What's fascinating here is how it all connects.
Right. Predicting space conditions. Makes sense.
Yeah.
And I'm guessing the main source of all this activity, the big driver, it's got to be the sun, right? Even being, what, 150 million kilometers away?
Oh, absolutely. The sun is, without doubt, the primary agent here. It's constantly active. It's always sending out radiation, plus this steady stream of charged particles we call the solar wind.
Solar wind, okay.
Yeah, and on top of that, it generates this huge magnetic field, the Interplanetary Magnetic Field, or IMF, that basically fills our whole solar system. It's like this massive, invisible influence everywhere.
An invisible bubble, influencing everything.
Wow.
Okay, so that's the constant stuff. But what about the big events, the sort of solar sneezes or something that cause the major space weather effect?
Ha, solar sneezes, I like that. Yeah, there are definitely more dramatic events. We track things like solar flares. These are really intense bursts of radiation.
Right.
Then you have coronal mass ejections, CMEs, huge bubbles of gas and magnetic field thrown off the sun. Massive thing.
Okay, CMEs. Heard of those.
There are also solar energetic proton events, SEPs, basically streams of very fast, very energetic particles, and high-speed solar wind streams, HSS. These come from specific areas on the sun.
So flares, CMEs, SEPs, HSS, quite a list.
It is. And when these happen, they cause big changes in the background environment out there. The plasma, the magnetic fields, radiation levels, particle flows. When this stuff hits Earth, it interacts with our own magnetic field, our magnetosphere.
Our planet's shield.
Exactly. And that interaction is what drives a lot of the space weather effects we see and feel.
Okay, so the sun's the main culprit, clearly. A very powerful engine. But you mentioned earlier it's not always the sun. Is there something else out there contributing? Here's where it gets really interesting.
It really does, because beyond our sun, we also have to deal with galactic cosmic rays, GCRs.
Galactic. So from outside the solar system.
Precisely. These are super high-energy particles, bits of atoms, really, that come from way outside our solar system. Think distant supernovae, maybe other phenomena in faraway galaxies. They can travel for millions of years to get here.
Millions of years. Wow.
And what's fascinating here, kind of flips things on its head, is how they relate to the sun's own cycle, that roughly 11-year cycle of activity.
How so?
Well, when the sun is at its quietest, we call that solar minimum, its magnetic field is weaker, offering less shielding for the solar system. So paradoxically, that's when we get the highest number of these galactic cosmic rays reaching Earth and the inner solar system.
So quiet sun means more danger from deep space.
For GCRs, yes, especially for astronauts outside Earth's protection. Conversely, during solar maximum, when the sun's super active, its stronger magnetic field pushes more of these GCRs away. So GCR levels are lowest then. It's this sort of seesaw effect.
That's really counterintuitive. Quiet doesn't always mean safe out there.
Not when it comes to GCRs, no.
Okay, so we've got stuff coming from the sun, stuff coming from deep space. Does Earth's magnetic field, our shield, handle all of this? Or do things get through?
It handles a lot, thankfully. That magnetic field deflects the vast majority of the charged particles from the solar wind and even some GCRs. It's a pretty effective shield.
They're not perfect.
Not perfect, no. Under the right conditions, especially during strong solar events like CMEs, a lot of energy and momentum can get transferred into our system. It basically overwhelms the shield temporarily in places.
And that causes...
It causes disturbances in our near-Earth space environment, the magnetosphere, the ionosphere, even the upper atmosphere. And these disturbances can have effects right down to the ground. We actually measure the level of that disturbance. That's a key part of quantifying space weather impact.
Yeah, this sounds like it could get serious, especially with all our technology.
Hmm.
So what does this all mean for us, for, everyday life? How does this actually impact things we rely on?
Oh, the impacts are huge and really diverse. Let's start with the big one, the electric power grid.
Right. How does space weather affect that?
Well, major geomagnetic storms caused by things like CMEs hitting Earth can induce powerful electric currents in the ground. These currents can flow into power lines, transformers.
And overload them?
Exactly. They can damage or trip transformers, leading to blackouts. Think Quebec, back in '89, a storm took their grid down in like 90 seconds. And it's not just blackouts. These currents can also speed up corrosion in long pipelines.
Wow, pipeline corrosion. That's unexpected.
It's a hidden effect, yeah. Then there's GPS or GNSS, the broader term for navigation satellite systems.
Okay, what happens there? My phone navigation going haywire.
It can happen. Space weather, particularly activity in the ionosphere, which GPS signals have to pass through, can mess with the signal accuracy and reliability. So, yeah, your position might be off, maybe significantly during a strong event. It can even shorten the lifespan of the satellites themselves.
Huh. Okay, so power, navigation. What else? Communications.
Definitely. HF radio communications, the kind used for long-distance stuff, especially by planes over polar routes or ships, can be totally blacked out during solar flares or radiation storms.
Blacked out completely.
Yeah, especially on the sunlit side of the Earth. Even a minor event, what NOAA calls an R1 radio blackout, causes weak or minor degradation. Stronger events are much worse. Even lower frequency navigation signals get degraded.
Man, that affects a lot. Aviation, maritime. And the satellites doing the communicating. They must be right in the firing line.
They really are. Satellite communications and just satellite operations in general face risks. Those high-energy particles we talked about, they can blast right through a satellite's skin and zap the electronics inside, cause glitches, phantom commands, even permanent damage.
Like tiny bullets.
Kinda, yeah. And then there's lower energy plasma that builds up charge on the outside, like static electricity, which can also cause problems and degrade components. Plus, satellite drag.
Drag. In space.
Yeah, during storms, Earth's upper atmosphere heats up and expands. Satellites in low Earth orbit run into more air particles than usual, which slows them down. They lose altitude faster and need more fuel to stay in orbit, or they could eventually fall back to Earth.
That's incredible. So many different effects. What about people in space?
Yeah.
Astronauts.
Big concern there, human spaceflight. Outside the protection of Earth's magnetic field, like on the moon or going to Mars, astronauts are much more exposed to solar radiation storms and GCRs. It's a major health risk that needs constant monitoring.
And even aviation. Pilots and passengers.
To a lesser extent, but yes. During really major events, radiation levels can increase even at aircraft altitudes, particularly on polar routes. Flights might need to be rerouted to lower latitudes.
Okay, well, that's a lot of potential disruption.
Yeah.
But it's not all bad, is it? You mentioned something beautiful earlier.
Ah, yes. The silver lining, you could say. The aurora. The northern lights and southern lights.
Caused by space weather.
Directly. When particles from the sun, guided by Earth's magnetic field, slam into gases high in our atmosphere, they excite those gases and make them glow. It's literally the interaction of space weather with our planet made visible. A beautiful consequence.
That is pretty amazing. Okay, so given all these impacts, from dangerous to beautiful, how on earth do we keep track of it all? Who's watching the sun in space?
There are space weather prediction centers around the world, but a key one, especially for the U.S., is NOAA's Space Weather Prediction Center, SWPC. They're part of the National Weather Service.
So like weather forecasters, but for space.
Exactly. They monitor the sun and the space environment constantly using satellites and ground-based instruments, and they issue a whole range of
Yeah,
products.
what kind of things?
Well, forecasts, obviously, like a 3-day geomagnetic forecast, outlooks for solar activity, even predictions about the solar cycle years ahead.
Okay.
They issue reports on specific events that have happened. They run sophisticated computer models like that Aurora forecast model you can check online to see your chances of seeing the lights.
Oh, cool.
Yeah, and models like WSA and LIL that predict when a CME might arrive at Earth. They rely heavily on real-time observations data streaming in from satellites measuring the solar wind, X-rays from the sun, things like that.
And based on all that, they issue warnings.
Precisely. They issue alerts, watches, and warnings, much like hurricane warnings. They use specific scales, the R, S, and G scales, to rate the severity of radio blackouts, solar radiation storms, and geomagnetic storms, respectively. This gives industries, power grid operators, airlines, satellite operators time to prepare and take action.
It sounds like a really dynamic field. Things must be changing all the time, new satellites, new models. What's the latest? What's happening right now in space weather monitoring?
It absolutely is dynamic. And yeah, there's always new stuff happening. If we connect this to the bigger picture, just recently, there have been some big steps forward. For instance, NOAA's Next Gen Observatory, SWFOL1, it actually just arrived down in Florida back in July, getting ready for launch.
SWFOL1.
Yeah, space weather, follow-on Lagrange 1. It's going to sit out at a point between Earth and the Sun and give us continuous, crucial monitoring. Better, faster forecasts are the goal.
That sounds important.
It really is. Also, thinking about human spaceflight, SWPC ran a big exercise this past spring tied into the Artemis 2nd mission plans, specifically to test and showcase their readiness to support astronauts heading back towards the moon. Huge deal for safety.
Makes sense given the risks we talked about.
Totally. And on a slightly more technical note, but cool for those who follow it, they just launched a new webpage back in June with much better imagery from coronagraphs, the instruments that block out the sun's bright disk so we can see the outer atmosphere, the corona, where CMEs come from, that arise on the sun.
So better monitoring, better support for astronauts,
Yeah.
better visuals. The field is definitely moving forward.
Constantly.
This has been fascinating. We've gone from what even is space weather to seeing how it's driven by the sun and even deep space phenomena like GCRs.
Right.
How Earth tries to protect itself, and the huge range of impacts it has on everything from our power grid and GPS to satellites and astronauts, and even giving us the aurora, plus how we're getting better at watching for it.
It really touches almost every part of our modern connected world, which, this raises an important question. Yeah, think about it. Every year, we become more reliant on space tech. Satellites for communication, navigation, Earth observation, global systems, all interconnected. So as that reliance grows, what does that mean for the future importance of really nailing space weather forecasting and figuring out how to protect against its effects?
So the better our tech gets, the more vulnerable we potentially become to space.
It's definitely something to consider. Our dependence is growing, so understanding and preparing for space weather isn't just interesting science anymore. It's becoming, well, essential infrastructure protection, something to keep thinking about.